Good day and welcome back to part 3 of our discussion on differentiating exponential functions. In our previous video, we introduced two key formulas related to differentiating e to the x and anti-differentiating e to the x. And recall, these are extremely convenient formulas. The derivative of e to the x is simply e to the x, and the antiderivative of e to the x then must be e to the x plus a constant. In fact, e to the x is the only function that is its own derivative. And in our previous video, we practiced some differentiation. Now we should go ahead and practice some antiderivatives. And with that in mind, let's go ahead and work through this first example together, and then I'll give you a few minutes to work the remaining two examples. When it comes to integration, we are currently in a very good position. As of now, we essentially have two different techniques or approaches. We are either able to directly compare the integrand or algebraically manipulate it so that we can compare it to our table of common indefinite integrals, or we use a substitution. Looking at this first example, I do not know the antiderivative off the top of my head. There's no obvious algebraic manipulations, and that leaves me thinking about trying a substitution. And when we try a substitution, our goal in general is to attempt to make u the largest possible inside function. So I would try 1 plus e to the x. That forces du to be e to the x dx. And note, we see that we have precisely an e to the x dx to play the role of du. So this works out extremely well. It is the antiderivative of the square root of u. And the square root of u, maybe more conveniently, is u to the 1/2. And I know I've reminded us multiple times, but recall the formula for anti-differentiating x to the n is 1 over n plus 1 x to the n plus 1, as long as n is not equal to minus 1. And I'll even foreshadow a bit that this case when n is equal to minus 1 is something that we are going to be able to take care of very quickly in an upcoming section. But for now, if n is 1/2, 1/2 plus 1 is 3/2, and 1 over 3/2 is 2/3. And once we've anti-differentiated, this is where we resubstitute. We want to put every u back in terms of x. So this is 2/3, 1 plus e to the x to the 3/2 plus c. And as a general reminder, this is more or less what your work should look like. So when possible, we organize in a single vertical column, and we use good notation. That is, we write our integral signs, we write our differentials. Once we've integrated, because it's an indefinite integral, we include plus c's. So I would now like you to pause your video, maybe give yourself 4 or 5 minutes, and evaluating these two remaining integrals. For the definite integral, let me remind you, when you use a substitution on a definite integral, you must change your limits of integration. So hopefully at this point you've paused the video, you've worked through these two integrals. And let me say at least attempted these two integrals. It's all part of the learning process. Now once again, the thought process. I do not know the antiderivative off the top of my head. There's really no obvious manipulations that are going to lead to a convenient integral for us. So let's attempt a substitution. And as usual, our choice for u is going to be the largest reasonable inside function we could attempt. So u equals 2 plus e to the x. That forces du to be the derivative of that, e to the x, times dx. And note immediately this works out exactly how we would like it to. Our integrand can be written solely in terms of u. It becomes 1 over u squared du. But as I claimed a moment ago, we do need to change our limits of integration. our original limits of integration are in terms of x. We need to make sure our new limits of integration are in terms of our new variable that we've introduced, u. And we can do this very quickly and efficiently by substituting those limits of integration into our substitution. So if x is equal to 0, the lower limit of integration, u is equal to 2 plus e to the 0, which is 2 plus 1, or 3. The upper limit of integration, x equals 1, becomes u is equal to 2 plus e to the 1, which is simply 2 plus e. And note, 2 plus e is a number and perfectly reasonable for us to work with. And now we go ahead and anti-differentiate. Note that this 1 over u squared is really u to the minus 2. Minus 2 plus 1 is minus 1. So we have 1 over minus 1, u to the minus 1, which is simply minus 1 over u. And we're evaluating this from 3 to 2 plus e. So we substitute in 2 plus e, we put a minus sign, and we substitute in 3. And it's perfectly fine to leave it in this form. For convenience, I'm going to write this as 1/3, the minus a minus 1/3, minus 1 over 2 plus e. And one last time, the reminder, when you are evaluating a definite integral with a substitution, you must change your limits of integration. And it really is a fairly quick and efficient thing to do. And note, once you change those limits of integration, you do not have to resubstitute. We just evaluate this equivalent definite integral in terms of u. The antiderivative of e to the kx is something that we will encounter frequently. You could go through the details of evaluating this with a substitution using u equals k to the x. I'm going to leave the steps to you, and I'm going to note that this antiderivative is 1 over k e to the kx. Something you could also easily check using differentiation. And it's always worth kind of reminding ourselves that indefinite integrals can be checked fairly quickly and efficiently with a derivative. If we differentiate 1 over k e to the kx, 1 over k is a constant that pulls in front of our derivative. And as we mentioned previously, the derivative of e to the kx is simply ke to the kx. That is, the k over the k cancel, and we're left with e to the kx. So I'll say check. We have now verified that when we differentiate 1 over k e to the kx, we get back e to the kx, which was the desired function. And this finishes our current discussion, and it leaves you at an opportune spot to practice examples. So if you have not done so already, begin working some of the suggested problems for this section, and if you have questions, do not hesitate to reach out. So stay tuned and take care.